So there was this question. Let's try this. So let me, I actually did not read it. So consider the following direct system of abelian groups where fix R and N and UN is Z for all N bigger than M. Okay, wait, but what is M? Uh, but is M also fixed in the question? UN. Okay, okay. Oh, sorry. Yeah. So UN is equal to Z. Sorry, and for N bigger than M, you have a map from Mn. So this and this multiplication by this, and we have to identify this as a subring. Okay, let me just write the question. So yeah. So this is a direct system. So yeah. So this UI or maybe UN. This is directed like this, where uh, UN is equal to Z, and there is this map for M. So for M less than equal to N, map from UM to UN, which is maybe I should say K going to R. R is a natural number, yeah, integer. R to the, yes, N minus M times K. Okay. Then the question is to identify uh, the direct limit of UN as a subring of Q. Okay. So eh, uh, okay. So you're saying that this direct limit, not direct product, it should be direct sum. Yes. So it will be direct sum modulo something. So what is that something? It will be the module generated by what? It will be module generated by maybe. Uh, okay. G alpha. Oh, right, yeah. So you're saying that I alpha is the inclusion of U alpha into the direct sum. Okay, okay, yes. I alpha of G alpha. Okay, I beta. Rho M. Okay, okay. Rho of alpha beta. Yes, and here alpha. Right. Yeah. So this is from the definition. Yes, that is, yeah, that is what I'm thinking. So you have n, so you are identifying these kind of things. So it's like 10000. This is identified with 0R00. Yeah. S- So there are two kinds of options, I think. One is you try component-wise multiplication and see, and one should be like the like treating them as formal power series and multiplying. Let's try them. Okay, let's try them and see. So yeah, I was trying to first identify if there is some meaning which to this, which we can you spot anything like that? Mm, So if I write n1, n2, n3. Yeah, so if I this does this look like some base R expansion? Some this one is like so I don't know. Yeah, no, nothing. Some like base R expansion of a number, but which number that I don't know. So yeah, right. So so it's like dividing this by R. So if I take n1 divide by R, then this is like n2. So where do we usually see this kind of thing? I don't know. Okay, so let's just try component wise multiplication and see if it is well defined. Right. So that should be okay, but okay. Subring of Q, right? So this dividing thing might make sense. Uh-huh. Okay. Okay. Right. So you want to just return a rational number. Yeah, okay. Z adjoint 1 by R. Yeah, okay, so that's the guess. Let's see. Yeah, so polynomial type. Yeah, Z adjoint 1 by R. Um, okay, so if we, yeah, then let's just try to map it. So if you have N1, N2 till NR, right, then you want to send this where? So maybe you want to send this to N1 plus N2 by R. Sorry. Okay. Yeah. Dot 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 NK R to the K, or K minus 1. Yes. So is this, that is what we have to check. So s- see, let's send this, then I will send it to N1, and if I take and this, then this goes to N2 by R, and so right, or if I, sorry, yeah, so if I take R times, yeah, so it's just easy. So it says this, then I will be sending this to Rn1 by R. So this is just N1. Yeah, so it is well defined. Right? So these two things are equal and they are going to the same thing. This is just a small check I did, but in general, you can check in the same way. Means, yeah, right. Let's do that. So let us check well definedness of. So we have, it is well defined. It seems now. Let's check it. So we have 5. So yeah, this is actually enough, because if you check well definedness on this level, then you have a map from the direct sum, and no, wait. So okay, no, so you should must have to check it. Okay, so this map was pi. So yeah, let's check it. Well definedness of pi. Okay, so you have to take something like n1, n2 till nk, and something which is related to this, but all the relations are generated by very um, simple things. So that would be, no, that would be right. That would be something like this, right? And everything else is same. Yeah. So all our relations, sorry, all the relations are generated by these kind of things. Only one step, if you just do, then the others will come. So now if you want to check these two are going to the same thing, then that just comes down to checking what I checked, that this thing and N1 are go to the same thing and they go to N1. So the map is well defined from the quotient. So then it is, yeah, then you have to check a subring. So you have to check injectivity. Yeah. So map is well defined. So we do, I'll just leave this and write on the next page. So we do have a map from the limit. Yeah, it's this is, you have to check the multiplication also. So this thing is, there is a map from here to Q, a map of a billion groups. Yeah. So the, yeah, so it is polynomial multiplication. But how do you, what's a good way to check that it's a ring homomorphism? Yeah, for that you have to put a ring structure. But now it is, we know how to put it because it gets induced. So let's write it. So yeah, nk, and similarly we have m1. Okay, I mean there are zero zeros like that, and you just, I think it's okay, right? I'll just leave it. It works, yeah. So that's okay. But just the injectivity, I'm a little bit concerned. So can you say, can how to prove injectivity? Show, yeah, let's think about that. Phi is injected. I think it will be better if we just provide the inverse, and we also know what the inverse should be, right? That's, I think that's that will be efficient. So inverse would just be as you know. So if we just send by the inverse. So I think if we just send this thing to just the tuple, but now we have to check that this is well defined because it's not obvious, I think. Yeah. And, s- so we should check that this is well defined. Yes, right. And yeah, and yes, and n1 and 2 nk is not zero in the quotient. Yeah. I think it will be best if you take the like no, if you take the like base r expansion of, so it's like you have this number, okay, but then you can rewrite this as some integer plus uh, plus a summation of this form where the k might now change, but these n2 to nk, they are all less than r, between 0 and r minus 1. Then the representation will be unique from what you all the things you know. And once then, if you just take that unique representative and send, then the map is unique by design, I think, right? Then the map is well defined by design. Yeah, then it is, yeah, because then you just send it to the direct sum and then you send it to the quotient from there. There is no problem. But here you're picking a unique representative, so it is well defined, I think. Yes. Yeah, so I think then it is fine. Yeah. So this is really the thing that you could guess. So that's what I was trying to do, but I could not guess that it should be this z adjoint 1 by r. What I may have done is like taken this and send it to this rational only. I don't see how I would have done it without this guess. So yeah. Yeah, makes sense. Hmm. Mhm. No, no, go ahead. Yeah, it makes sense only to, because, and now of course now that I know it, so it sounds okay. But like, so if we just like send n1 to n1, and then we want to send let's say 0 n2, yeah, 0 r n1 to also n1. So that basically means that I should send this to this. Yeah. So then this you would get this if you just try to make it a well-defined map. Try to send. So basically, if you try to send n1 0 0 0 and 0 whatever rn2 or rn1, like try to send this to the same place, then you will end up with this map. Yeah. Anyways, it's the same thing. Hmm? That I don't know. Yeah, that's a good question. Let's write that. Right. So, so let's say that R is a subring of Q. First is how does it look like? Then we can say if it's a direct limit or not. So you are inverting R. You are inverting R from Z. Okay. So yeah. Just, so it's like you're taking it's like so you're taking Z and you are oh see yeah. What I mean is that you're so this is like this. R will contain Z, right? And you are inverting an integer R. Okay. So that basically means that you are doing what is called localization, if you like, right? With respect to R. Okay. But so what that just means is like you're taking this multiplicatively closed take Z, and you take this multiplicatively closed set. I mean, just like it's closed under multiplication, and now you are how to say call this S, right? And then you are formally constructing a ring like this, where you are defining where you are just under with the understanding that these kind of this with the understanding that this is understood as n by r to the k, and using that you put relations on this. So using this you put ring structure on z cross s, right? And this is what is r, what this r our r was, right? Now the claim is that every subring is like that, right? Something like that. So yes, because it's very clear, because you just now you take an arbitrary subring. So you take this arbitrary case and you just collect all the denominators of the elements. It's like, so if you just take no, is that a good yes, that's fine. You just take this where m by n is in R, right? Take this collection. You see, this is a multiplicatively closed set by design because R is a ring. So now, now the claim is that again, so the claim is that this R is gotten from Z by this kind of procedure. And that is also clear because R is basically that, right? Every element of R is of the form m by n or n in S, right? Or sorry. Should write n here. Okay. So this with the appropriate relations, is basically R. Okay. So that basically means that now this thing is basically saying that this is 1 by n where there are multiple of them. I mean, right? This is R. Okay, all these things are same. I mean, at least it's convenient. You may have to prove the things, but that's how it will turn out. Now we can come to your question, right? Whether this is the direct limit. So okay, so the first question I would ask is, can you reduce this to finitely many n's? Can you reduce this thing to finitely many n's, or do you have to keep infinitely many n's? Because I fear maybe if there are infinitely many n's, then it might not be a direct limit of. Okay, no, no, you just want a direct limit of integers. No, no. I think the answer might change, because if it's an infinite set, then usually it's a. I mean, that is just a very vague thing. If it's an infinite set, then it's. I don't know actually. Oh no. So if well, so if you take polynomial ring in infinitely many variables, all right, I think it should not matter because that's also a direct limit. Yeah, sorry, it will not matter. The direct limit answer should not change. So maybe we should not think whether it's finite or infinite, and we should try to answer if this is a direct limit. Yeah. The slightly thing that I was confused with is, oh, well, like power series. But even if this is an infinite list, your expressions are still finite at a time. Every expression is finite. So I was sort of forgetting that. So yeah. So it's not like an inverse limit. But anyways, coming to this. Uh, yes. So your question is this a direct limit of abelian groups? Right. So that should be true. It should be true. But yeah. But what abelian groups do you take? Well, of course, you can just take this the abelian group this itself, right? So that's not a very interesting answer. But then the question should restrict. Maybe is it a direct limit of of z's? Yeah. So yeah. So the question. Uh, yeah, that is okay. That is right. Right. So you're saying we might use that to further to okay, okay, okay. So let me try to. Yeah. Yeah, and here it will be integers only. But here we won't need those other cyclics. So yeah, so you are saying that if you can write this as a direct limit of integers of abelian groups, then you can also write it as direct limit of integers. Mm, yeah. Uh, yeah, I mean then it's done, right? Because then you just write this as a direct limit of GIs. Okay, maybe not direct limit of GIs. Yeah, sorry. So the GIs are finitely generated abelian. Of course, everything is countable, so that's okay. So this thing, this thing is this thing. But somehow the now the way I am doing this, it's losing its charm, kind of. It seems like something is going away. Yeah, but still, that's true. But so this GI is finitely generated, and because you are inside Q, so they won't have the other cyclics. It's torsion free, so there's no torsion. Yeah, so it is like this, and yes, and then you can just write this as a direct limit of finitely many z's. It doesn't hardly matters. So the answer is yes, theoretically, but this is not a nice expression or anything. So the answer is yes, you can write it as a limit of z's, as a direct limit of z's. But if you want, but again, if you want to write the explicit thing, this is not the way. This is just answering the question, but I mean, the problem is that it might be difficult to write because these ends, they need to be, you have to check some independence between them and so on, right? In order to know, in order to nicely describe those maps. And I think that might not be possible because I mean, again, it comes to primes and factorizations, and I don't think it would have a nice way. But I would still like to think if you can. No, because if you just take primes, infinitely many primes, then you cannot reduce it to finitely many ends. So that is also out of the picture. So yeah, answer is yes, but I don't think any nice expression will exist other than it's when you're only inverting one element. Yeah, yeah. Okay. Yes. And this is this kind of thing where you take an integer, you take a ring, this integer z is a ring, as a ring, you take a ring and you take a subset which is multiplicatively closed, or you take a subset and generate a multiplicatively closed set, and you invert those things formally by this procedure, roughly I've said, is localization, and that's an important way to identify what is going on. Like basically that's what you identified here. So it's good without that it's localization. Okay. And basically this, I mean, this localization can also be written in this way, but yeah, maybe think about that. Yeah. No, no, yeah, but yeah, we can think about it. Okay, or maybe so you can try, but it's like you see what I'm saying is that like this particular thing also, right? You could have written this as like z with infinitely many variables, one variable for each n, and then put the appropriate relations, right? If you could you then so you could have written this thing as a quotient of this infinite polynomial ring, right? Just like so, what I'm saying, like what happened here, you had this thing, which I said is a localization, but you can obviously write this. This is the same thing as this with with of course with this minus 1 equal to 0, right? So this with this relation, right? So I'm saying that every localization can be, every time you localize a ring with respect to a multiplicatively closed set, you can just, so for example, if you had these kind of things, uh, yeah, if you had this kind of thing, then you can also write this as, the number of variables would be like depending on this. So infinite polynomial ring, everything is a quotient of infinite polynomial ring. Any commutative kind of thing would be a quotient, roughly speaking. And then you can just then you just put the relations, like just put the relations, so like this. And this is just nothing. I just formally writing things. Yeah. Okay. And yeah, and basically if you look at this more closely, actually from here you directly get the direct limit expression, right? Because this is like, as an abelian group, this is z uh, infinitely many times appended, right? And can you help with this? How do you write this in this form? Yeah, because it's, yeah, let's see. So if you're writing xr equal to 1, then what does that mean? Yeah, it means that this 1 is of course just 1000, right? And this xr is, this x is 0. This x is 0 comma 1000, right? Is this times r, and these two are equal. And then you see that this is what we were looking. So maybe I put a minus here, and yeah, yeah. So you're getting this. So from this relation, you have got this relation. And in this way, you will get the other relations also. So you directly get the direct limit, yeah, through this exploration. And then you can just do the same thing here, but now you can see it will be more cumbersome. So yes, it is a direct limit of integers. Now you can see that directly, right? Because again, this will be integers, of direct limit of integers, but the maps will be cumbersome. Or I, yeah, yeah, I mean, write it. I don't know if it will be, or it seems to me, but Yes, seems to me it will be cumbersome, but I don't think I don't see any point in trying to describe it. Yeah, as you can, it doesn't sort of answer any new question, seem to answer anything. If I describe the maps more carefully. Yeah. Okay, so this is, I think it's an interesting question. Twisted in a twisted way, it's written. Yeah. Yes, I don't know much shift theory, but yeah, direct limits. What from what I know, they're of course used. But yeah, like I think once we were discussing, so so if you take a sheaf and then you fix a point and then you try to define the basically try to make sense of the possible values the functions can take at the point, which is the sections, the possible values they take at the point, then that's called a stock, and that's a direct limit. So yeah, and it's used in other places also, I suppose. Yeah, because yes, yeah, it would should be. Yeah, a direct limits are crucial. Yes, yes. So in a way, you are. Yes. Um, yes. Useful question. Yes. So from the example you gave, right? So basically, like you said that every group is a direct limit of finitely generated subgroups. It's finitely generated subgroups, right? So it's like now it's like if you want to prove some fact about a group and you know it for its finitely generated subgroups, then you could use this thing, right? But how would you make a better example? An example would be good, right? So an actual place where you could not do without direct limit and it's yeah changes the game. So yeah, so for that you yes, because most of the examples we see are like bookkeeping. We use it just for convenience. Yeah, like just to say like this localization thing we did, you describe it using direct limit, but direct description is even better. Okay, but let's see. So yeah, yeah, so yeah, one very nice thing is this. So there is something called Pontriyagin duality. Okay, and I'll just take a small part of this. I don't know it very well either. So I take a small part of this and try to say why direct limits are important. So you take the integers. Okay. So if you think of it as a topological group, natural topology, the discrete topology. So now if you take the maps, all the continuous maps from Z to S1, you see that this is S1 in some sense. So it is a homomorphism, but continuous group homomorphisms. Okay. So is this something that is clear? So it's like you have to just see where one goes, right? So yeah. So this would be S1, right? But then now the duality comes. So now if you take and now this you take this S1 which you got, and then you again take the home with S1. So that this S1 is fixed. Okay. And that thing is so if you take again, then you actually get back Z. Now this might be more difficult to see. So let me try to explain this. So first of all, what this means is all homomorphisms, group homomorphisms from S1 to S1, which are also continuous. Okay. Yeah. And Yes, and I think you have done these problems, right? You once I think so. The point is that uh, uh, yeah, so every phi is basically we think of S1 as R modulo Z. So it's like pi going to e to the power I n theta. These are there, right? These are certainly we discussed this kind of thing, and we kind of proved that these are all that everything is like is like this. And of course, we did it in a longish way, but conceptual proofs are there. But we know a proof, so it's good enough. This is basically saying that that these form some kind of a basis for any nice function, any nice periodic function on R. So these are Fourier, these are the basis, and the coefficients with respect to this basis will be Fourier coefficients, which can be written in terms of integral and so on. But now you see, the point is that there is a duality. You started with a group and you got back the group after taking home twice with S1, with this S1. And so the claim is that if you take any reasonable group, which is in this case locally compact abelian group, but I'm not going into that because I my things to explain this application of this. Then this thing gives you back G. This is the claim. This is considered to be a hard theorem. Okay. Now, yes, yeah. So okay, for all G in locally compact abelian, yeah, and these homomorphisms are continuous and group homomorphisms. And after, I mean, you have to wonder what topology will you put on this, because you have to view. Oh, sorry, I wrote some very wrong thing slightly. I mean, I have to take the home again, right? Yeah, did write that. So then you get by this is the claim. And of course, for to make sense of this, even you have to sort of understand, think about what should be the topology on this. Then only you can think of it as a topological group and then take. But all those are technical stuff. Those are the different things, and it requires some other work. But we have this. Now, if you want to prove this, let's say, okay, the question would be, for what have you proved this? So you have proved it for Z, right? And by this direct sum home and direct sum relations, you prove it for Z to the n, let's say, right? So Z to the n, so this home, I will write as home S1 and then home S1. Okay. And so this is the notation. And this, by this kind of things, you can then prove that it is just S1 cross n times. So yeah. So we want to prove this Pontriyagin duality, let's say, for all locally compact abelian groups, but you have only proved it for discrete. These are discrete groups, right? So you have proved it for discrete and elementary. These are called elementary. So you have proved it for this collection of groups. Okay. Now, in order to extend, right? So now to show, going to the full locally compact abelian requires many more steps. But now to show, but even to go from this to show this for all discrete groups, how would we go about it? Let's think about that. We are not going to full LCA, but just a discrete groups. So you have proved it for those kind of discrete groups. Now, how would you extend the proof formally without doing much more mathematics? Means just by formally, how to go to all discrete groups. So here here now we would have to come up with a statement like this, that every discrete group is a direct limit of um, of elementary discrete groups. So the GI are elementary discrete, which by that I mean that uh, GI is equal to some Z to the n or some finite group. Those also you can prove this duality easily. Even for those, in fact, the dual itself is themselves. So it's not a surprise also. So this is one of the claims. Right. Just a second. Assume that you have proved this claim. Okay. That let me just see how to prove it. Second. Yeah, because just we actually, in fact, we use this only, right? So you see, like if you take a discrete group, so you take let this be let this thing star, let the star be the thing that we accept, we know. So you take G there to be a discrete group. Now a finitely generated discrete subgroup. So what is a finitely generated discrete group? It is this kind of things, nothing more than that. Right, that is fine, right? Because just by the structure theorem, it will be a direct sum of these things. Or am I saying something? Ah, right. I mean, fine. And also you need the locally compact. If you put the locally compact condition, then you will get that the finitely generated discrete groups are only these. Otherwise, you can of course say where is Q? Q is also discrete, but it's not finitely generated. But then that's not in this picture. Q is not here. Q is I mean, sorry. Yeah, Q is here, of course. Q can be here. But then if you take, okay, sorry. So if you take finitely generated discrete group, then the claim is that it is these things. We can prove that later. Yeah. Now that you know this, so from we get this. Okay, now the claim is how to move forward. Okay. Okay. And then there are some basically now we will use this. So how we'll use this is like this. From this, we make this kind of claim that this category, so we consider this category of, so you see what we are trying to extend the result, right? So we consider this category for which we have proved it, which is the C naught is the category of elementary discrete groups. And then there is this category of discrete groups. Okay. So this is elementary discrete, and these are all discrete. So using this claim, we can say, we can make a statement that this category is a dense subcategory of this. Okay. Now I have to define what dense means, but let's say, okay, so this is a dense embedding. And so C, I'll just write this. C naught is basically the subcategory generated by these kind of things. Okay, so where N is this kind of thing, and C is a category of all discrete, and of course locally compact and appealing. Okay. So now from that statement, we want to make a dense embedding sort of kind of statement. So how to do that? Yes. And at this point, it might look a little unnatural. Yes. So we want to say that from this category of discrete groups, you can get a functor. Let's call it F. So basically, we just want to say that a discrete group can be written as a direct limit of elementary discrete groups. We want to say it more categorically in terms of functors. That's all this is going on. And then I'll just call that thing dense. Okay, and then we will use it. Because once you call it in a certain way, then you can use some package, some other theorem. Otherwise, you don't know how to code some other theorem in this case. So that is one of the issues. So yeah, so I'll say that from the C, there is a functor to some category, and that will be the category of diagrams, which is sort of the diagrams whose direct limits you're going to take. Category of diagrams in C naught. And then there is a functor going this way, which, you know, what you do with a diagram, you take a direct limit of a direct system of diagrams. Okay, such that this composition, and this is, I'm just restating that thing categorically and nothing more than that. such that this functor is naturally isomorphic. Well, this is what this means to the identity functor. All this is just saying is that if you take a group G and apply this functor, how to construct that functor is not difficult. Just write the finitely generated subgroups and arrange them in the obvious way. In this case, it's obvious, but in some other cases, which I did not say, it's a little more interesting. And then you take pass to the direct limit. All I'm saying is that this is isomorphic to G with some other naturality condition, but this. Okay. So now from there we got here. Now what is the benefit of this? That is the question. Okay. So what this does, now we'll say this a little briefly. What this does is like this. Is if you look at the so you look at this row, okay, which is let's just take Z, okay, and now row Z. Now what is row Z? Is this, okay? Maybe it doesn't. It's this will be so simple that you will not be able to maybe see the point. So let's just say it like this. So what is this? You see, you want to prove an isomorphism, so you should first have a map and then show that it is an isomorphism. That's the usual way. So what is a map? So, well, you see, like vector spaces, right? So V sits inside its double dual, or it's even equal when it's finite dimensional. So basically, you take an element of G and you send it to you send it to the thing, which, so you know what it does. It just takes a linear functional and evaluates it at G. Right. So that kind of, so let's just call it eval. It's not important to know the detail of this map, but it's just the evaluation map. So my point is that we have this evaluation map for every group G. Okay. And this evaluation map can be thought of as a natural transformation between two functors. Right? It's like, right, because what you're trying to do is show an isomorphism between two objects. But we don't do it like that. We try to show an isomorphism between two functors. That's the better way. So what this rho G is doing, so I'll just try to say here, is that you have this category LCA, and you have two functors coming out of it. I'm used to drawing this diagram, so I'm drawing it. Two functors. One is the identity functor. It just takes a group G and just sends it to G. And one is this functor twice hom functor. Okay. And you have this rho G, right? Why do we say this is a natural transformation? That you probably know that if you have an H and you do the same thing, then you have this naturally. Now, if you have any morphism phi, and then you get this value phi, it's a functor. So the double dual thing also acts on the morphisms, and it gives you. These details are probably not important here. Yeah. So, but still, this is the thing. Okay. Now, what is the point? So the thing, maybe I should say like this, is if you think of this as C naught, and then you like the larger category, this dense in according to our definition. C. Okay. Now for C naught, for objects in C naught, we have shown that these things are an isomorphism. So we have shown that these two functors, this functor, and let's just call it chi square, this functor, because chi sort of dual twice. We have shown that these two functors are isomorphic, which means that just means what we said, that rho G is an isomorphism for objects in C naught. Now the question is, how do you get isomorphism for objects in C? Right. That is the thing. So you want to take some other group outside, like Q, right? And you want to show the isomorphism for that. Okay. So you would like to say something like this, that this natural transformation, because the functors all still exist on the larger level also, right? But you want to show that, you want to say that, and this is where the density, this is where that thing will come, the limit thing, is that this natural transformation extends uniquely. That's the kind of thing you want to say, right? This natural transformation, there is only one way to extend it. You want to say that, not this, you want to say that any natural transformation defined on this, wait, no, maybe not any, yeah. want to say this natural transformation only has one extension. That's the first thing you want to say. And how does the limit thing help you? That is the thing, right? So yeah, so first you want to say unique extension. I mean, you already know there is there is an extension, right? The row, this thing itself has an extension. I mean, this is a restriction of that row, because for any G, we said that there is a map from G to G double hat, right? So it has an extension. So, but you want to first say that there is a unique extension. It's a mathematical style which works into work. So I've read in that way, as I'm saying. So you will say that it's a unique extension. For how do you say that there is a unique extension? So you say that if rho hat is an extension, okay, then what does rho hat do? Rho hat uh, gives you a morphism from, let me not use Q, you might be distracting, from H to H double hat. That is what rho hat does, where H is outside C naught. So this is what H does. It is an extension. Now you know that there is that functor F, or basically that you can write. I think I did not need to say like this, could have directly said. Basically, there is a, but let's see, there's a functor F, right? Which you can use to go to the diagram category. Okay. So what that means is that you can apply this functor F and now get a map between the diagrams. Okay, between the diagram, and those diagrams are made up of finitely generated groups, finitely generated discrete blah blah blah. Okay. So how to say this? Yeah, let's just call it the diagram for H and the diagram for H hat hat, which will be same, but we don't know at this point. We cannot assume that. Okay, and you know that these diagrams are made up of finitely generated things for which the theorem is, for which the thing is an isomorphism. Okay, so the point is that yeah, now how do I say that there is this map? Yeah, okay. So I want to say that this map, this induced map, is made up of those rows. Okay, of these rows, right? Because you see in this diagram you would have something like Z and some other things, right? In the diagram. For diagram for this, you will also have some Z and these things. And the map that you will get will be a restriction of this rho hat in somehow. That will be the case, right? But the restriction of that rho hat will have to be this row which you started with, because it's an extension. Right. Right. So it, yeah. So it means that these are isomorphisms because the theorem is true for the so that's we use the density. That's why it's dense. Now because an isomorphism, now if you apply the limit thing, because the limit is a functor, it will take isomorphism to isomorphism. Okay, but then when you take the limit, you get back H, because that's what the claim was, that it's you get back G. So you have proved the right. Whoever did it proved that in this way. So we see that you have proved it. So see how the limit thing really helps, right? Yeah, I think it really helps. Otherwise, it's. I mean, this the idea will still be there. That yeah, I mean, if you proved it for all elementary groups, then every discrete group comes from elementary groups. But in what way does it come? Using direct limits. Okay, then we abstractly prove things for direct limits and apply it here. Okay. Yeah. So I think this way, yes, and this way this way they prove it for compact groups also. From elementary compact groups, they prove it for compact groups. And so basically, it's a very nice. What they're doing is basically that from small bit of actual mathematics, in the sense that the internal structure and theorems of these objects, small bit of that, and then lots of formal, like whatever can be done formally, you do it formally. That's kind of the idea, right? So you don't do analysis, you don't repeat the same integration again and same kind of thing again and again. That's it's very nice. So in this way, you can prove this called Pontriyagin duality for all of yeah. This was from a paper This is from a paper, uh, Reuter, uh, Reuter. Um, yeah, category theory applied to Pontriyagin duality. It's just, I suppose, yes, yeah, because I got it from the internet, so it was category theory applied to Pontriyagin duality. Yeah, and inverse limits do even more miracles in some way. Inverse limits are even more because they completely change the nature of the object. But since you ask for direct limits, because direct limits seem more like a bookkeeping business, but they're still quite convenient. As you can see. And basically, then studying the functorial properties of direct limits, like so if you have an exact sequence of direct systems, let's say if you have an exact sequence of direct systems, because you can make sense of exact sequence of direct systems, basically exact at each level and for each object, exact and so on. Then when you apply the limit, do you get exactness? Eh, Yes. So we have these direct systems, right? And we have an exact sequence of direct systems, which means so these direct systems are indexed by the same poset, right? So then you can make sense of the exactness because just for each object you have ith object in each, and there's a direct the maps are form a direct exact form an exact sequence. So that's a direct system, and then that's an exact sequence of direct systems, short exact sequence of direct systems. Then you can take the limit, and then you can ask if this will remain a direct. This will remain so this will be modules or whatever, wherever you are, and this thing will it be exact? Again, will it be exact or not? Right? So for modules, it is exact. So this is like if you look at chapter 2 of Atia MacDonald, then he in that book they ask these questions. But why I'm saying is these questions are so important that certain categories are defined where so the property of the category would be that a direct limit of exact short exact sequence of direct systems is exact. That will be an axiom. Okay. And it will turn out that considering those categories is extremely fruitful. Yeah. May gives you access to the things you wanted to talk about, right? Something like that. Yeah. So those are so with this and some other conditions, what you get is called a growth index category, and it includes a module category of modules. Okay. But considering the growth index categories, which are not module categories, you might actually learn things about the module category. So yeah. Yes, because abelian groups are modules over Z. So it's a statement is included in that sense. Abelian groups are modules over Z. So if you say that statement for R equal to Z, then you get the statement. But it's true for many other things which are not modules. And I don't know much, but it's quite interesting. I wanted to read, but I never got around to reading it. Yeah. Yeah. Is it true? The problem is that I don't know if you have direct limit in the category of rings. Oh, you do have, right? Or you tell me, I don't know. I yeah, but I don't know if it will have a unit, right? I don't know, like if you just take z and take the direct sum, doesn't it will not have a it will not be unital. And then if it's not unital, then I don't know what 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 can happen to it. Then God knows, I don't know. Yeah, but yeah, you can still think about it. I don't. Yeah, it might have. I mean, yeah, I think it will because you see, I mean, you just think of rings and they you can just think of them as Z algebras or Z modules, right? So because it is the question of exactness, the question of having a ring structure is one thing, but the question of exactness does not depend on that, right? Yeah, so it should might be true. Yes, might be true, but you should take some examples and see. So the category theory and these things are quite useful. Yeah, but the point is that these are useful, but this is like formal. This is formal business. I mean, you don't get any credits for this. I mean, because what the credit is that like later if you have to if in some other situation, if you feel that something is built out of something, then what is the mathematical notion of that intuition of built out of? Coming up with that is the key, right? Because like, because sometimes you say the group S6 is built out of D3 and C2, but how? Not as direct product, as semi-direct products. So coming up with that is always the problem. Yeah, is always the ingenuity thing. Yeah. Okay. These are the kind of things. Yeah. No, no, I didn't do anything in undergraduate. No. But one should try to do. Yeah. Yes. Yeah, the problem is that in pure mathematics, usually there are no options, no explicit options. By explicit options, I mean if you are going to apply to some formal summer research program, then usually it is just a reading project. Okay. So you take someone else's work and you read it. Yeah. But since mathematics is so specific, so if you individually understand where you are and so on, and suitably write a mail to someone, you know, and if they can understand that they have something which you can work on, then that may work. Yeah. Right. So that is the way. If you want to do something, if you want to do something new, you have to say that thing in a proper way, be able to write that thing in a proper way. Like, you see my point, like this is particular thing I'm reading, and I'm doing this, and I feel that from here I can do something new. Then the professor has to see if there is something new, if he has some problems, because the main thing is the problems. Where are the problems? Like, I don't know if there is any problem that you can solve. I don't know if there is any problem that I can solve. I don't know the correct problem. So finding that, you have to express your things, and then the professor has to see. And that is a very hard thing, and that is why we need guide. I mean, for PhD also, it's very, where is the correct problem? With any problem I pick, either it is done, or it is too difficult, or I don't know. I don't have motivation. I don't know. It's very strange. I keep getting stuck in, I read something, and then it gets too hard, or it is too boring. Whereas, okay, okay, I don't know what that is. So what is experimental mathematics? What? Okay, but what is a Hodge diamond? Okay, okay. Oh, okay. Yeah, Hodge diamond I've heard, only heard, but yeah. Yes, but it's good. I mean, because I think through experiments only you can find patterns, and yeah. Otherwise, theoretically, you can find things, but my feeling is more and more that it's better to find through experiments and maybe physics or something. Otherwise, it's not. It's just at the end of the day, some, like, you solve some questions, but it doesn't have any implications uh, outside what you do. Like, I'm saying, for the person who is doing just getting the intuition from mathematics itself. Yeah, but I don't know. Yeah, maybe so if you get some result, you can explain me one day. We can see. Yes, yeah, maybe that would be better. Yeah, so you can just from scratch explain first time, and yeah, because Hodge things are of course there, very important. There is Hodge theory, you may have heard, of course, but I have never studied them. Yeah, and in fact, the Hodge, it's called a Hodge construction, or the something that requires lots of functional analysis. Yeah, which I know from functional analysis. Yeah, but yeah, let's see. That's good. That's good. Yeah, but then if you want to do some theoretical stuff, there, like research, then you should do like this. Yeah, like ask some professor. See, yes. Because I mean, at the same time, like, while experimental things are good, only experimenting will also not be. Yeah, like that should be a small part, a part of the thing. Yeah, it's a mess. It's a confusion, which is I don't know how to resolve this. What the correct way to do? Okay. Yes. Yeah, this is I don't know how one gets to doing research. Yeah, and I'm never able to get. I think the only time I can do it for me is when I get like paid for doing only that. Like like when you start a PhD and then you have to do one thing, stick to one thing and do research. Otherwise, it's quite strange for me. Don't know. Yeah, you do one thing, jump to see. I mean, you read and see, but in sheaf theory, I don't know how you can start solving problems. Yeah. There were right. Yes, these things. Yes, yes, yes. Right. Yeah. Yeah. There is something called directed. Maybe next class we can talk about it. Directed sheaf cohomology, which is which is sheaf cohomology, but it's very recent. But it's done on some graphs and something. So yeah, that is something which I also wanted to understand. So maybe we can look at it together and see if you can read because that's a very recent thing. So and it's applied in probabilities and so on. But yeah, because someone else also wanted to understand, and I told them that I will see it, but I never saw it. So maybe we can see. Yeah. Yes. Yeah. Because I mean, those kind of things is something where you can maybe see some new because shift theory already people have done everything in that. So and, yeah, I don't have much hope. Yeah. Okay. 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 Then see you. Huh? Bye. Yeah. Bye. Thank you.